Recording has started.
Okay, so yeah, okay. Thank you. I want to thank I thank both the organizers at the LCL Math and also the organizers of the Fellowship of the Ring to giving me the opportunity to speak. So the new results are all joined with Ilya Smirnov. We have actually started this project a long time ago, and but actually none of us have been working actively on this in the last couple of years. But we do have plans to finish this this year. And so on the positive side, I think it's I've heard several people saying you should really give your talk earlier because after you finish a project, you feel boring about it. So that's okay. So okay. So throughout my talk, all rings are commutative. And Noetherian is one. And so okay, so our motivation is all coming from Lech's inequality. So let me just first recall you this theorem. It's a very old result of Lech. It says Rm is a local ring, and I is a M primary ideal. So then there's a inequality relating the multiplicity and length of this ideal. Then EI is less than or equals to let me say d factorial times the multiplicity of the ring times the length of R mod I. So here d is the dimension of the ring, and so this is Hilbert semi-multiplicity. So let me just recall you. So EI is the Hilbert semi-multiplicity. That's, you can define it as the limit n goes to infinity. It's sort of, you look at the Hilbert function of I and you look at the normalized leading coefficient, the length of R mod I to the n. So this is a polynomial of degree n. You look at the normalized, polynomial of degree d. You look at the normalized leading coefficient. Okay, so that's the Hilbert semi-multiplicity of I, and this is just my shorthand notation for the Hilbert semi-multiplicity of the maximum ideal. Okay, so that's the Lech's inequality. It's a very classical result. And so let me, okay, so just in case you are not so familiar with this, I give some examples indicating, okay, let's just do some sanity check. This inequality makes sense or is valid, all right? So, so let's just think about what happens when I itself is the maximum ideal. So of course, in this case, the left-hand side is E of M, so it's just ER. So that's the left-hand side. And the right-hand side is, this number is 1 and is d factorial ER. Well, it's sort of silly, but that's true. All right. And you could do some other thing, right? So for example, let's track this asymptotically. In other words, let's track this for a power or sufficiently large powers of an ideal. Or for some t, let's just use n for n very, very large. So then in this, let's track this inequality. I plug in this large power, and we know this is the same as n to the d ej. Well, what about the right-hand side? Is d factorial. Let me just make sure I got it right. ER. That's the right-hand side. Okay. So the inequality says I should have this, but let's just check what is this asymptotically. So asymptotically, when n is large, at least, so d factorial times this just by the definition I gave you, for this Hilbert semi-multiplicity is n to the d ej. So this too, asymptotically, is n to the d ej. But I have an extra term. I have an ER. And it's well known the Hilbert semi-multiplicity is always an integer at least one. So again, you get somewhat like trivial inequality. Okay, and just do one more example. So I think this. Let's just do some real examples. So these are okay. So let's just take a say a polynomial ring over a field, and so let's take I to be an M primary and integrally closed monomial ideal. And so in this case, the point is that for monomial ideals, there's a formula for multiplicity and the length. It's just you can read off the multiplicity and length of a monomial ideal using the Newton polyhedral. All right. And so in this case, okay, so again that theorem says I should have EI less than or equals to d factorial. The ring is regular now, so there's multiplicity is 1, ER is 1. This is what the Lech inequality asserts, but in this situation, this is just d factorial times the volume of the Newton polyhedral. Or complement of Newton polyhedral. Of complement, sorry. Well, this one is just the number of integer point inside the complement, right? So this is the d factorial times d factorial times the number of integer point. In the complement of the Newton polyhedral. Okay, so now this inequality, this is not entirely obvious, but so in this case, the Lech inequality comes down to a very down-to-earth question in convex geometry. You can just check. Okay, so hopefully are there any questions about this inequality? Okay, so so our goal in this work is to, well, we are motivated, highly motivated by this, but what is our goal? So as you can see from this at least, okay, let's just look at these two examples. So you see, the inequality is actually far from being sharp, right? Because here, in this like simple example, I have an extra d factorial factor here, and this in the second example, I have an extra ER term, which is make this sort of far from. I mean, at least if you multiplicity is large, this seems like far from being sharp. So so it seems natural to just introduce an invariant that sort of measure the sharpness of this inequality. I erase the theorem, but I will. So once I'll write down what. I mean, once I write down the definition, I'll quickly recall you what the theorem inside the content of the theorem inside the definition. So here's the definition we made. We say the quantity. We call the quantity. So our notation is CLM, or we define this to be just the supremum among all the M primary ideal. R is a local ring of this EI divided by d factorial the length of R. Okay, so that's our definition. So what does LM stands for? And oh, good guess. Okay. Yeah, you know that, but yeah. Actually, when we were writing this paper, Ilya, I want to call this something else, but I strongly insist we use this. Yeah. This is the Lech Mumford constant. Okay, it's gonna. Let's hold on for a second. I'll show you why Mumford is involved in all these things, but it's gonna, let's just try to be patient for a little bit. So, okay, so, but let me just do a remark. So first of all, I still keep that example here. So, okay, so what is Lech's inequality here? So Lech's inequality is basically saying, okay, so EI less than this number times the multiplicity of a ring. So this invariant is always less than or equals to the multiplicity ring, and this is exactly Lech's inequality. All right, because I recall you the theorem that I just erased. Just interpreted in this literally the same. Okay. All right, and this is always bigger than or equal to 1. And so why is that? So this is actually by example 2, because I take the supremum of all these ratios. In particular, you can take I to be the large enough powers of some m primary ideal, and in that case, asymptotically, right? So this ratio, this ER is sort of a waste. Asymptotically, these two are the same. It's just a basic definition of multiplicity. So this, you can see this by looking at I equals to j to the n for n sufficient enough, because the bottom thing just sort of asymptotically, it's the same. Asymptotically, they approach 1. And since I'm looking at supremum, so this I plug in that family, j to the n is approaching 1. So this supreme must be at least 1. Okay, so it's just a trivial remark. Okay, so and all right, so and our interest is just try to sort of, okay, so there are several things you can ask now, right? So this is an invariant sits in between 1 and the Hilbert-Simon multiplicity. And so we want to say this is somewhat of some way of measure of singularities. So we can ask, like, how do you compute this? But it turns out it's very difficult. So I'll show you some examples. But you can also ask, when is this equals to 1? And when is it equal to reach the maximum possible value? And so the first result I'm gonna present here is that at least we can answer one of them. So first of all, we can answer, when does this equals to this? Okay, so one is the Lech's inequality really sharp. So let's see. So this is the first theorem. It's due to it's already proved by Hunicke. This is Hunicke, myself, Fan Honghui, and Ilya Smirnov. But we did it in the equal characteristic case, and then Ilya and myself handled the mixed characteristic case. But the theorem says the following. So you have this number is the maximum possible value if and only if one of the following happens. One of the following holds. So first of all, it's always true when the dimension of R is at most 1. This is quite easy to see because the D is 1. So you plug in the maximum ideal, you got the multiplicity of the ring, basically. All right. And the interesting case is the second case. So it reaches the maximum also when the dimension is at least 2 and the multiplicity of the reduced ring is 1. So first of all, I put this is M-adic. Okay, maybe I should put this remark at the very beginning. So this invariance clearly, So this invariant is stable under completion because there's a one-to-one correspondence between m primary idea of R and m primary idea of R hat, and all these invariant that I care about is stable under this completion. So it's a variant. It's really an invariant about the completion. So we're not going to do the pathological rings. All rings will be excellent, for example, right? So whatever condition you put here, it's natural to put conditions on the completion. So in this case, it's just so when the dimension has these two, so this invariant got the maximum possible value if and only if you take the completion modulo the neo-radical, and then you got multiplicity 1. Okay, so for example, if R is regular, so then, but that's already sort of clear from here, because if R is regular, this is 1, so you certainly got the maximum possible value. Okay, so this is the first thing, but I mean, it turns out we are really interested in the other way around. We really want to understand why this invariant is equal to 1, turns out. I'll show you some reasons. Okay, we want it to be as small as possible, turns out. Okay, so okay, so let me just, I'm not allowed to use that board. That's so bad. Can I hide something for the online participants? Okay, so the question is, one is, no, it's fine. So sorry, I was just, yeah. Okay. For the moment, there's one example that there's one situation this holds, namely when R is regular, or more generally when the multiplicity is 1, because you see that's one case this will happen. So, all right, so I put down some examples that we can compute. Hopefully I'll come back to them later on. So, okay, so for regular rings, this invariant is always 1. And so we hope this carries some information about the singularity. So we try to some baby case. We try some like small types of singularities. And okay, and also in dimension at most 1, this invariant is also not interesting because it's just the Hilbert-Simon multiplicity. So the first thing we're going to try is a rational double point. So like the hypersurface of dimension 2 and carries rational singularities, turns out things like that. And so let's just try some. So this is the stuff we can compute. Okay. So this is the AN singularity. Well, the other one that I really like is the sum of the cube, cone of elliptic curve. And I'm going to put on one more. All right, just give some examples. So it turns out this invariant is 1 and actually this is true for all rational double points, not just this type AN. This is 3/2, and this is 8/7. Okay, so, and this one is actually not due to us. This actually, we just reformulated in terms as a result of Goto, EI, Watanabe. They sort of, I mean, they didn't introduce this invariant, but they just improve Lech's inequality in some sense for these two-dimensional rings. And this, I just reformulate the result in this language. And these are due to myself and Smirnov. Okay, and so these are already not easy. I mean, both of these cases require some work. But I also want to just give you some feeling like how hard this invariant to compute. So you can take the same singularity, but you are joining one more variable. Okay, and similarly here and here. Okay. So any guess what is this invariant is? No guess? Craig, you know something about this, right? So, anyway, so it turns out it's okay. You don't want to make a guess because you are all smart because we don't know how to compute it. So this is one, and I don't know this. Turns out, okay. But I know some information about this one at least because well, I'll come back to that later. What? Say that again. I don't think this is this, but I don't have a proof, unfortunately. I think it should be easy to rule out these are the equal. But, yeah. No, not always. Even for regular ring, it's just regular ring of dimension at least 2 is gonna never. Oh, that's a good question. I'll come to that. Okay, so.
Maybe you have to repeat the question if I don't hear it.
Oh yeah, okay.
On the Zoom.
So Justin's question is, do I know whether whether these cases are different from this number or this number? I don't think I know. I don't think I know, but I don't think they are the same in these cases. And Shree's question is in this definition, is the supreme always attained by some ideal I? And the answer is no. So there are examples that I mean, there are some questions along that direction we still don't know, but in general, the answer is no. And what's your question? Oh, Mumford. Oh, Mumford. Oh, God, sorry. I forgot this fuse medalist. Okay. So, yes, I will, but give me like 5-10 minutes. I'll come to the big name, but all right. So, okay. So hopefully I show you some evidence. Okay, that this is an interest, but I want to basically convince you for the rest of my talk. Actually, by the way, this is a 1-hour talk. I'm not gonna make people annoyed at me just giving 1.5 hours. It's supposed to be 1-hour talk. So I don't know why on the schedule they say like 2 to 3:30, but sorry. Okay, so so for me, this invariant, this Lech-Mumford constant, sorry, I didn't finish that sentence. So for the rest of my talk, I basically want to give you some reason to convince you that this is an interesting invariant to study, and its connections to different. It has applications and it's connected to different questions that I'm interested. So first of all, let me mention Lech's conjecture. Okay, so this Lech's inequality or this number is really marginally related at least. Okay, so what is this conjecture? So it says the following: if you have a flat local extension of Noetherian local rings, if then you have an inequality on the Hilbert semi-multiplicities. To this day, this is still wide open, but even though it's quite simple to state, it's still we still don't know the general case. And why is it related to this Lech's inequality or this CLM that I introduced there? So first of all, let me make a remark. So first of all, it's well known that if you want to prove this this conjecture, you can always assume the 2 rings have the same dimension. So we may assume the 2 rings are the same dimension. Okay, so then let's just what I want to do. So I want to compute the multiplicity of the maximality of A expanded to R. So that's an M primary. So since I made this assumption, this is an M primary ideal. Okay, so I can talk about this. And by this Lech inequality, or by the way I define this CLM, so this number is now less than or equals to d factorial times this CLM. Remember, CLM by definition, by design, this is just the optimal number that I should put on here and the length. Right? If I use this number divided by d factorial times the length, I got the supremum I got is this number. This is by design. And of course, I know this is less than or equal to multiplicity. Okay, so this is less than or equals to let me just keep it like this. But by this assumption, by this flatness thing, it's a little bit of work. You can show that actually this is equal to the multiplicity of the base ring A times the length. All right, so this requires a little bit of work, but it's more or less just coming from the flatness assumption here. Okay. All right, so now you see I have this less than or equal to that. I can cross this term now. So what I got is that right, so the conjecture asked for a comparison between multiplicity of the base and the multiplicity of the target. We got something like this, right? And remember, this is always at most ER. So you get a very weak version of the conjecture, namely, we cannot really say this, but at least at the expense of multiplying by d factorial, you have a very weak version of okay, so all right, but now okay, so the advantage of introducing this invariant now is just I hope the purpose is clear. For example, let's just do a dream. Okay, so the naive dream is that okay, maybe this invariant is less than ER divided by d factorial, but then you win because so naive hope. Maybe would it be possible that in some cases at least this is just less than or equals to ER divided by d factorial? But clearly that's not possible because ER could be less than that. I mean, this number is that should be at least 1, right? I already told you. And what if the multiplicity is small? You cannot hope that much. Okay, you just can't hope that much. But it's still yep. Yep. Yes, if this number is 1 and you are in this situation, so then E of A is at most d factorial. Yes. So Mark's question is that if CLM is 1, then I got an inequality EA is at most d factorial. I think the answer is there's nothing wrong with that, but you are putting a strong assumption. Your assumption is that A has to have a flat local extension whose target have CLM 1. CLM equals to 1 is a very strong assumption. Oh, at least I'll come back to that. Exactly. Well, that's clear from the definition because if you remember CLM by design, maybe I should just put this thing, is the supremum of EI d factorial the length, right? Plug in the maximum ideal, ER divided by d factorial times the 1. That has, if this is 1, then ER is at most d factorial. Otherwise, it's just exceeding. Go and erase this. But okay, so let's just think about what is this naive hope? What is this? Because I'm just introducing this invariant, but what is this really saying? This is just saying, I mean, if you unwrap the definition, this is saying I'm aiming for a sort of a much stronger inequality, namely EI less than. I just ignore the d factorial. All right, so this is equivalent to that because I just removed the d factorial from the other side. Okay, and this is too much to hope for because, as I told you, this sometimes sometimes this number is 1, but the multiplicity could be small. So this is definitely not going to be the case. But this is not totally the end of this connection, because if you want to attack this Lech's conjecture in this way, at least because I'm applying this. If you want to just attack the conjecture this way, you can see I'm applying this inequality or whatever to a very special ideal, namely the ideal extended from a flat extension below. Okay, and such ideals are indeed very special. Let me just put down this question here. So again, Rm is local ring. And I is M primary. And such that I can throw in one more assumption. So this is called strongly Lech independent ideal, but I'm not introducing it. I'm just tell you what it is. You can, and so if this is basically this is saying like I put some strong assumptions on I, but this assumption is satisfied whenever your I is coming from a flat extension below, because it holds for the maximum ideal here, and under a flat extension, everything is preserved. Okay, you can ask for this very special class of ideal whether you can hope for this inequality. Then is it true that EI less than or equals to ER? Whether in this situation you can remove the d factorial term. Because if you can, again, you prove the conjecture. So this question a positive answer to this question implies a positive implies this next conjecture. This is at least like I don't know any counterexample to this. So this could be one approach. So, but I don't know. And there are some positive evidence. This is due to Ma. So a couple years ago. So this question, indeed, the question is true. In the graded case. So it's not totally an absurd question to ask, but it does have some strong evidence that this should be true. Okay, so that's one of the reasons why I care about this CLM. It has some connections with the conjecture of Lech. Any question so far? There are more reasons I'm going to convince you that this is an interesting invariant. So, okay, so now finally, the Mumford's name has to come into this talk. So, so let's back to this CLM, this Lech-Mumford invariant. So this is a geometric reason why you want to care about this invariant. So Mumford, in this GIT paper, he proved the following theorem. So suppose you have a polarized projective variety over a field. So over a field, algebraic closed, something like, and suppose this polarized pair is asymptotically Chow semi-stable. I'll say more about this. Okay, maybe I'll say some words about this now. So i.e., what does this mean? So this means if you, okay, so if you use a high enough power of L to define this projective embedding, okay, I use a high enough power to embed in the projective space. A very large projective space, depends on the sections of L to the n. So then saying it's asymptotically Chow stable is saying that, okay, so now I have a closed immersion of X into the projective space. And so now I want the Chow form of this X under this large enough embedding is semi-stable under the natural action, under the SL in-person action. Okay, so this is all for all insufficient large. Okay, so asymptotically, the Chow form is, if you look at the orbits under this, you want the zero is not in that orbit. So that's the definition of asymptotically Chow stable. And Mumford shows if you are in this geometric setup, so this is everything. We put some global assumption on your projective variety, but then he showed then for every point, close point on X, this invariant. Of course, he didn't phrase it this way, but I'm just saying what he proved. Then this invariant for the stock, the local ring of the variety adjoining a variable is 1. Okay, so that's the connection with the geometry, and I think partly motivated by this thing that he can prove, he introduced the following definition. So now the definition is we're back to the local world. So here's a definition. So again, so everything is local, the Noetherian local ring. Rm, so this is called, first of all, this is called semi-stable if it's satisfied this. If this invariant after adjoining a variable, a power series of variable is 1. So basically semi-stable singularities is exactly those that could possibly shows up for the singularities of the asymptotically semi-stable varieties. And he, so what does stable mean? Sorry, this is going to be getting a little bit technical. So the semi-stable is very easy. It just means this invariant after adjoining a variable is 1. And stable means it has to be stronger than semi-stable. If it is semi-stable, and the supreme in the definition is not attained. That's exactly what you pointed out. And the sup in the definition of this CLM, adjoining a variable, so basically like 1 is not attained in this setup. Okay, so these two definitions are both due to Mumford. Ilya and I gave another definition, but just what about CLM of R itself, not adjoining a variable? We call them Lech stable.
When is 1, does it remain 1 when you have the
No,
variable?
that's exactly the point. It's very hard.
Changes.
Exactly. It's very hard to understand. I'll give you examples. It's very hard to keep. So the interesting part of this invariant is that it's not stable under adjoining a variable. And that's exactly why this is very interesting in our opinion. Okay. Any question about the definition? Sorry, I'll give you examples and more comments or more remarks. I'm gonna say that on this board, but you're okay. So Lech stable is stronger than stable, and stable is stable obviously implies semi-stable by design. But this turns out implies this. Okay.
So if it's Lech stable, when you add the variable, it does remain one. That's what you're saying. If it's one,
yes,
the variable does.
Yes, because one is
usually it's not preserved, but
right.
if it's one, it remains one.
Right, because one is the smallest possible value.
Exactly.
Yeah. Yeah. Well, maybe any other questions? Okay, so
when you add a variable, can you decrease?
yes, you can.
Does
you
it
can.
decrease?
Oh, the question is, when I add a variable, can I decrease? What happens? You guys have to be patient. I'm going to give you examples, but yes. Sometimes it does not drop, sometimes it drops. So, yeah. Okay, here's a lemma. Again, this is in Mumford's paper already. So first of all, when you add a variable, you're not going to increase this invariant. Okay, and so this property implies, because it only drops, possibly or stays the same, this Lech stable implies semi-stable at least, all right? But you can say actually a little bit more, it actually implies stable. Well, I guess dimension at least one. Okay, so okay, let me give an example. First of all, let's just think about regular rings, okay? So what about K? A field, okay? Well, the invariant is obviously one. It's not very interesting. If you're joining a variable, it's also one. If you're joining more variables, always one. Okay? Is the sup attained here? It is, right? Because it's one. So for DVR, the supreme is attained here. That's why it's very strange. So the field is not, a field is Lech stable under this definition, but it's not stable because the sum is attained. But once you, okay, so this is, so if you goes up dimension, let's just say you look at K double, so that, let's say this is your R. R is the DVR of dimension one, okay? It's still semi-stable, it's still Lech stable because, this CLM, no matter how you join the variable, is always one, okay? But this is, I claim this is stable now. If you are joining another variable, the supreme is not attained here. Turns out, it's an easy exercise. Just think about the colength and multiplicity in a regular local ring. As long as the dimension move up to 2, you cannot attain 1 here, even though asymptotically is 1. But you cannot attain 1 here, okay? So that's why I put in this little assumption here. Okay, but regular rings are basically, they are nice, they are stable, Lech stable, semi-stable, whatever. So, right, so let's just look at on the first example. Let's look at CXY quotient XY. This is the node in dimension 1. Dimension is 1. So what is this invariant? Remember, in dimension 1, this invariant is not interesting. It's just the multiplicity I already told you, right? So this is just the Hilbert-Sandwich multiplicity because we are in dimension 1, okay? And that's 2, so it's not Lech stable. But if you're joining a variable, I claim things change. So this is, now I'm going to look at Cxyz mod xy. I mean, even in this case, you have to do some work. It's not obvious. This is 1. Okay. So it is semi-stable. Is the sup attained here? Well, let's look at this ring. This is my ring, now dimension 2. So let's plug in the maximum ideal. What is EM? Modulo d factorial times the length. It's 2 factorial times the length. Okay, so that's one of the ratios shows up in the sup, right? Multiplicity is 2 divided by, this is 1, so it's 1. So 1 is attained here, so it's not stable. So this is semi-stable, but not stable. Okay, I'm not saying this is trivial. You have to do some work to show this ratio is always less than or equal to 1 in here. Okay. All right. So any question? And so Mumford did one more case along this line. So you can, well, this is a simple normal crossing or whatever node in dimension 1. You can ask an analog in higher dimension. And Mumford is, of course, when he writes the paper, he's mostly interested in surfaces. So he, you can ask about this. And Mumford showed this one is semi-stable. Again, this is not obvious. So this ring, I mean, okay. So what does he really have to show? He had to show if you are joining a variable. Right? Remember, semi-stable means that's invariant, but you look at the ring of joining a variable. So this guy has this Lech-Mumford constant 1. Okay, and that's the work you have to do. And by the way, this ring is not this is obviously this is not Lech stable, right? You plug in the maximum ideal. This ring has dimension 2. What is this? Now the multiplicity is 3. So you already got something strictly bigger than 1 since this CLM is the sup of all these things. This is already not Lech stable. And in fact, the supreme in this case is this. Requires a work to prove. The CLM is 3 half, turns out. And so we did the general, sort of the higher dimension. And at these 3, take R to be this Xn quotient out by just the simple normal crossing of maximum possible. Let's take the product of the variables. So what we showed is that all these things, this is actually stable, but not Lech. Okay, so for all these things, if you compute the invariant of this ring itself, is always, I claim is always strictly bigger than 1. But if you're joining a variable, you always got 1. And in fact, it's slightly more, is you got 1 and 1 is not achieved in this definition of sup.
You know what actually is invariant?
No, God knows, I don't know. I don't know this. It's very hard to compute. Well, this case might be, but I don't. No, I don't. Yes, it's all about integral closure. Yeah, to compute this invariant, to compute the sup, you can always restrict yourself to integral closure. Yeah. Okay, so in the last 10 minutes, let me show you, well, we have some, well, mostly we did a lot of computations, but then we can prove a connection with the singularities of the MMP. So, but let me just first recall you the MMP singularities, some of them. Okay, so this means, sorry, I just changed the. So if you have a, I'll just keep my setting really simple. So this is finite type, or essentially finite type over C, and say normal Q Gorenstein. The canonical divisor is torsion. And so since I'm in characteristic 0, I can take a resolution of singularities. Actually, I want to read out the log discrete, so this better be a log resolution. And let me set E to be the reduced exceptional. All right, so I'm just giving you the definition. So then the ring R is called canonical, or R has canonical singularities if the relative canonical is effective, and R is log canonical. If the coefficient in this oh, sorry, yeah. Yeah. Ah, okay, okay. If this relative canonical is, well, basically this is effective, and here I want the coefficients is all the coefficients at least one. So, but equivalently, since I have this exceptional plus the reduced exceptional is effective. Okay, so that's how one way to define this log canonical. So clearly this implies this. All right, so okay, so now what we can show about this. Here is a theorem. It's the same setup, so I'm just gonna work with finite type, or essentially finite type over a field of characteristic 0, normal Q Gorenstein. Sorry, I'm just repeating this. So then we can prove two things. So first of all, if R is semistable in the sense that I just defined, so then R is log canonical. Okay. Two, if this invariant on this ring R itself is 1, if R is Lech stable. Remember, this means the invariant after a Jounian variable is 1. This means the invariant of this ring itself is 1. And but this is not. I also have to assume R is isolated singularity. Then R is canonical. Okay, so these are our main result. Is so the connection between this semi-stability and this MMP, this is not we're not the first to observe this. We are largely, I should say, we are largely inspired by this work of Odaka and also partly by Chen-Yang Xu. So basically, okay, what does these people show? So okay, I already showed you. So that okay, remember Mumford's theorem says if you're in a global setup, if you have a projective already, So if you have a asymptotic semi-stable variety, so then what Daka proved is that whenever I have put this global condition here, or stability condition here, so then the singularities are log canonical. I guess I need sorry, normal and Q-cut. So it's just, I just do this in simplest setup so you can define this in this Q-Gornstein case. And remember Mumford, I put this theorem here, but I erase. Mumford shows if you have this global assumption, so the singularities are semi-stable. Okay, so this is a very classical result of Mumford, it's 1970s, but this one was not observed. So this one proved in 2012. It's actually quite late after already. Okay, and what we observed is that, so now they are like these can be defined for all. I mean, these are purely local properties. It shouldn't have any global thing. So what we showed is exactly this. Well, that's the first part of this. Okay, but our techniques is quite mimic Odaka's techniques using this running MMP, pick a suitable modification, and then do the computations there, because all the multiplicities or whatever colengths can be read off using Riemann-Roch on the using some like intersection numbers on the modification. Okay, so finally let me come back to this. So now at least I can give you some. Okay, we don't know. I said I still don't know this number. I'm very interested if someone in the audience can help me compute these. But all right, so what we know now, right? So this one is x squared y cubed z to the 7. This is not log canonical. It's like the log canonical structure is 1/2, 1/3 plus 1/7. That's strictly less than 1. But this one is not log canonical. You can also just resolve it and then just do this very, straightforward. So this is not log canonical. So the theorem says this ring has this constant has to be, well, I don't know what its number is, but I know this at least 1. It's strictly bigger than 1. Okay, and this is not surprise because actually in Mumford's paper he already tried to compute this, and he said with David Eisenberg we made some computations. He can show this is bigger than or equal to 1.00067. They picked some very complicated ideals. They just estimated that they got this number, and then they show this is strictly bigger than. But now I have a theoretical explanation why I don't know what this number is, but I know this is not going to be 1. Okay, but this so this one is log canonical. Okay, so this is not. Let's just see. So this, okay, if I ignore this, this is the cone of elliptic curve. This one is this is one not canonical. This is isolated singularity. This is not canonical, right? Because well, it's you blow up the discrepancy is exactly 1. The relative canonical is exactly 1 in this case coefficient. So this one is not canonical. So what I know from the theorem is that the CLM of the ring itself is strictly bigger than 1, but this is not a surprise because I erased this here because this one we know how to compute. This one is actually 3/2. Okay, so we know how this is not a surprise. But I have a joint variable, it is log canonical, so our theorem says nothing. I should say that the converse is definitely false, because if you want to have semi-stable or Lech stable, there is an upper bound on the multiplicity, for example, d factorial, as you pointed out. But these singularity could have arbitrary large singularity, could have arbitrary large multiplicity. So there's no hope of reversing this arrow. And so this guy is log canonical, but you cannot say it's semi-stable or whatever. So that's why I'm getting stuck here. If I were to guess, I would think this is 1, but I don't know whether that's true. Okay, I really think this should be 1. And Mumford also seemed to have some indication that this should be 1, but it's hard to sort of extract what he really meant in this paper. But okay, so I think I will stop here. Yeah.
Are there any questions here, at least for Linquan?
Just a couple. So Mumford did name these, right?
Right. Mumford didn't name this. Mumford called them flat multiplicity, and he used the notation E0,
Right.
which I feel sort of confusing because that for me is Hilbert coefficient, so it's not.
Well, and EK, and that led to my second question. You're only adjoining one variable. So he adjoins many.
Right.
And
Yes.
it could eventually go down to 1, right? But you don't.
Actually, no. Actually, in order to prove this, we need to join a bunch of variables. We have to use the higher the invariant also. Yeah. So, and this one is like if this is semistable, well, not semistable. If CLM, if this is 1 for some n, then it's not enough.
What if the limit is 1? You know?
I think that's also true, but I don't have a proof. I don't want to say something, but that's my speculation, but I don't. Yeah.
Any other question?
So do you know when this equal to ER over D factorial when M computes a supremum?
When the maximum ideal compute the I don't know. That's a good question. No, I don't know. So it has to be. So if you want right, then the multiplicity has to be large. So in order that EM over D factorial computed. But yeah.
One more question. Yeah. I just don't remember. Shaw classified like 2-dimensional semi-stable or something. What did Shaw actually?
I think she, right? Is it she or
Shaw? I think J1 Shaw.
Right. Is it a she or he? I'm not
Oh,
she. So I think Shar is I think Shar. Okay, so first of all, she just in the surface case, and then the result is that she has. It's very similar to this. She assumes semistable, and then she gave a list of candidates. I mean, if you are semistable, then it must be coming from one of the lists. But all their lists are log canonical, so it's just compatible with the theorem. But it's maybe a little bit more because, as I said, the converse is not true. You have to put multiplicity bounds or whatever. So the classification in dimension 2 is better than just saying they are log canonical.
There are no other questions. I didn't see any in the chat. There is a question. Can you pass this?
I just want to know, you calculate this example as 3/2. Like, what goes into that calculation? Like, how do you calculate that?
So these for surface so if your thing inside is a surface, so what we do is just I really have to check, but I think what we do is that we take a minimal resolution, and then we use Riemann-Roch to compute the intersection number upstairs. So all this multiplicity and colength can be read off in terms of intersection numbers upstairs, and then upstairs there are some obvious inequality. But those things give you some estimate, and then we have to guess out like which one compute this. For example, in this case, the maximum ideal compute that, and in the 8/7 example, some other ideal computed already. So you have to guess out the ideal first, and then show all the other ideal give you less than or equal to that number. That's the way we prove. Yeah, it's definitely related to that. But, yeah.
Which one again? Thank you.
Thank you, everyone. I'm going to stop recording.